you all here, and I'm really glad to welcome Dr. Frank Drake back to Green Bay. I'll say a few words about him. I didn't prepare any words, but I'm going to say some words anyway. And I want to say, first of all, that when Frank Drake first came here, this was his first academic home, so welcome home to Green Bay. Job after he graduated with his PhD from Harvard. He came to Green Bay first. And I'm imagining that he took a look at that 85-foot telescope out there, which was the only one that was completed at the time, and he started to rub his hands together and say, I wonder if this telescope could detect extraterrestrial intelligence. And so 50 years ago, he set out to attempt to detect signals from extraterrestrial intelligence in what we now call the first real modern search. He made this search for ET science, and he's still at it today. And the last thing I want to tell you is that when Frank Drake did that seminal experiment back 50 years ago, we knew of no other planets around any other stars except for those in our own solar system. And now there are 400 extra solar planets that we know of. A year later, in 1961, Frank came up with this very cool equation that was the agenda for a meeting that he called together to discuss the probability of life in our Milky Way. And this event today marks the beginning of a new meeting that we're going to have to talk about it some more 50 years later. So without further ado, thank you so much for doing this, Dr. Drake, and let's give him a big welcome.
Thank you very much, Sue-Ann, for that introduction. And it is really a very special pleasure for me to be back here in Green Bank. I indeed came here in 1957. Sue-Ann wasn't here, so she's got the facts a little wrong. The 85-1 didn't exist. The entire observatory was still a farmland with a few farmhouses, and that was it. And there were three of us, myself, David Heshin, John Findley, and Beatty Sheets, key person in our operation, in a little farmhouse at the observatory. And from that, now, a little more than 50 years later, 52 years later, we have the magnificent institution which the Green Bank Observatory is today. My years at Green Bank were some of the happiest in my life, and I always look back at them with great pleasure. So it's very nice to be here and to tell you about the search for extraterrestrial intelligent life, which, as you were just told, was started 50 years and 4 months ago here at Green Bank with the 85-1 after it was completed, 1960, April 16th, and we've got another failure, I see. Oh, no, that's me.
That's not you.
That's me. Yes.
Oh, it is.
My computer thinks it should turn off after a certain time. But I'll be going through these slides, I think, fast enough that shouldn't happen again. Anyway, it's really a great pleasure here for many reasons. So this is one of my favorite places in the world. I often think of it as my real home. But other places since, but I still think of Green Bank as my home. And it's wonderful to be able to celebrate the 50th anniversary of the start of a search which in the long run will be very important to everybody on Earth, the search for extraterrestrial intelligent life. Now, what we're searching for, of course, is life on a planet somewhat like the Earth, And in the old days, 50 years ago, we thought the planet had to be very much like the Earth. It had to be at the right distance from its star so that the temperatures were right, that there would be liquid water, because we know liquid water is essential to the development and evolution of life, particularly the evolution of technology using life. And in a way, this was somewhat limiting. In our first search, we looked at stars only very much like the sun. We thought they were, very much like We looked at stars very much like the sun because we thought they would be possibly the abodes of life. Since then, our ideas have changed a lot, and we've come to recognize that some of our old ideas, which is that planets have to be just like Earth and the same distance from their stars that Earth is from the sun, are really not right. And as you'll see here in a few minutes, we've learned a lot just from our own solar system. Now, what should you search for? This was a question back in the late 1950s. A lot of thought was given to it. It's a little dim, sorry about that. It doesn't help you, it helps me. There were things you could think of that you might search for. One was the lights of cities at night. And this is, in fact, a combination of photographs from spacecraft showing what the Earth looks like at night. And you see the lights of cities. That's what those lights are. If I go to the next slide, we home in on North America. And you see what's there. Now, we could expect cities to have lights for very long periods of time in space. Those lights should always be there in some way or other, so perhaps this is what we should look for. And we thought of doing that 50 years ago. But if you do the calculation of how large a telescope, an optical telescope, you need to detect these lights, you discover that the telescope has to be, with our current technology, at least about 5 miles in diameter. That's a little tough to do, Green Bank or anywhere else. 5 miles in diameter, beyond our abilities at the present time. You might have to put it on the far side of the moon, someplace like that, or in space. And so that was not promising. Another thing which was popular then and still today is space travel. Should we send spacecraft to the stars? Or perhaps are the extraterrestrials sending spacecraft to us? Now, our current spacecraft go about 10 miles a second. And that sounds pretty fast to you, but it is fast. You don't want to be going down the highway here at that speed for very long. You'll never make it around the next curve, I'll tell you that. But at that speed, as great as it is, it takes about 500,000 years to get to the distance of the nearest stars. So our present spacecraft certainly wouldn't do, but should we think about whether the extraterrestrials might use this? After all, the science fiction movies tell you they come to us easily. You just dial up Scotty and say warp 7 and you go from one star to another. And the time it takes to give a commercial on TV. Could it be that way? Well, in fact, the laws of physics are not that flexible. And in fact, high-speed travel in the universe at speeds approaching a good fraction of the speed of light are extremely difficult to achieve, and in fact so difficult, it's not likely, it's a funny statement, that any intelligent civilization would do it. Only a dumb one would, and they don't know how. Now, just to show you, we actually know the design of the ultimate rocket. This is the most powerful, energy-efficient rocket you could build. It only has two tanks. One of them holds ordinary matter, which is the matter we're familiar with on Earth. The other holds antimatter, which is something we have made a bit of in our atom smashers. And that is matter in which the protons are negative and the electrons are positive. That's the only difference. No big deal. But very difficult to make. In fact, to make it, you have to put as much energy into the matter as Einstein's equation requires, E equals mc squared. So I'll see in a minute that is very difficult to do. Well, how does this work? When the matter meets the antimatter down here, we know from both theory and actual experiment that the matter and antimatter annihilate each other and all the mass of the fuel is converted into energy. E equals mc squared. So this makes this the ultimate rocket. There's no way you can get more energy out of any kind of matter. The exhaust of the rocket is actually a blast of very high energy light, what we call gamma rays. So this is the design, and it can approach the speed of light. Wonderful. Now there are little problems. One of them is, where do you get the antimatter? As I said, that's very difficult. The other is, what do you build the rocket out of which can simultaneously hold matter and antimatter? It can't be made out of matter because then it will be annihilated by the antimatter, and it can't be made out of antimatter because the matter will annihilate it. So it's a technological challenge. We have a name for it. It's called mutability, unchangeable material. But of course, probably such a thing does not exist in the universe. But should it be, we are not quite right enough yet to have invented it. You could build a rocket like this, very simple, basically. How much would it take to launch a mission of perhaps 100 colonists and use a rocket which is designed to go 7/10 the speed of light? Why that number? That's the speed at which, if you're traveling according to the laws of relativity, you think you're going at the speed of light. Well, the design has been done. Here it is. Notice all the dust on this slide. This goes back 50 years. That's why the slides are getting kind of dusty. We used a staged rocket, as we do in all of our high-speed space missions. And this was to have a payload of 1,000 tons. That's the weight of the rocket and all. It goes somewhere into space at 7/10 the speed of light. Well, what does it take? Even with the stages, the total amount of mass, almost all but 3% is fuel, weighs 34,000 tons. That's what it takes to get up to 7/10 the speed of light. How much energy does it take? Minimum, this is with 100% efficiency, to convert matter into antimatter, 33,000 tons, half of that, 60,500 tons of antimatter. Turns out to take 500,000 years of the total electric power production in the United States. Hope you heard that number right. 500,000 years. You have to shut down America for 500,000 years to launch this mission. And by the way, it doesn't come back. This just gets it there. So that's why I said that only dumb civilizations would try this. Well, what might work? There are great distances between the stars. We want to find out things. We want information or something to travel as quickly as it can. As quickly as it can in our universe is the speed of light. Well, what does travel at the speed of light? Electromagnetic radiation, radio, light waves, infrared waves, and such. It travels at the speed of light. It cannot carry matter, but it can carry information. And so you quickly learn that an interstellar contact, conversation, whatever you have to do, the right way to do it is not what you're looking at here, but to use electromagnetic radiation and to send information. Maybe that's all you want to send or need to send. Or if you actually want to send something, you send the instructions on how to build whatever it is you want to send. And this way you can do things at the speed of light at very low cost because electromagnetic radiation is cheap. Well, I'm just telling you that now the logic that existed in 1959 when we first embarked on our first experiment here at Green Bank to detect extraterrestrial life, and it resulted in a 2-month search on what's known as the 85-1, which is the telescope you come to if you drive down the main road at the observatory, the first big one. This was the first telescope built at the observatory, and here we see it. It still looks the same today, pretty much, except this part's changed some. And these are the people that did the experiment back in 1960. Those of you who've been at Green Bank a long time will recognize many of them. One of them is still very active, Fred Cruz. He was the chief telescope operator. This is Omar Boyer. George Grove is here somewhere.
He's on the end.
On the end, yeah, thank George. And Omar Boyer was part of the gang, and this was the crew that did the experiment in 1960. We had then very crude equipment. This was the equipment used in the project, which was known as Project Ozma, named for the Princess of Oz in the Oz books. And why that? It's because it was a euphonious name, but because the land we were looking for was a land far away, populated by strange and exotic creatures that hard to reach. If you read the Oz books, that was a description of Oz. No transistors here. This is all vacuum tube electronics. No computers. For any of you who are less than about 20 years old, you may not believe there was a time on this earth when there were no computers. But that was the case. And here you see it. Oh, vacuum tube electronics. Key item was this radio receiver. This is an amateur radio receiver which we use as a way of cheaply achieving tunability. We could monitor one channel at a time. Just one channel. The data was recorded on a pen and ink recorder here. And being optimists, we had this. Does anybody recognize this? Yeah, about 6 people recognize it. How many people recognize that? Oh, living in Green Bank is healthy. We're at the right end of ages here. There's a Wollensack tape recorder, which we reel-to-reel tape recorder, which we had connected to the system because we were optimists. We thought, well, maybe the extraterrestrials are talking to us and we want to record this first conversation. So this was standing at the ready. Well, this was used for 2 months. On the first day, we actually received a signal while the telescope was pointed at the star Epsilon Eridani, a near twin to the sun, about 10 light years away. That was very exciting. It was recorded on the Wollensack tape recorder. And we wondered, is it really this easy? I mean, that practically every star in the sky was transmitting. But before we could verify that it was actually coming from space, and that was radio interference, the thing would fight here, why you can't use cell phones here and can't drive your cars with your telescope. It might be that. And it took a few days before we were able to detect the same signal again and could show it was actually coming from an airplane. It was, for some reason, flying around Green Bank, sending a signal which was like none we'd ever heard before. It was a signal that sounded like, heard it then several times, never heard it since. You think it was some kind of military transmission, but it was definitely coming from a plane. Well, after 200 hours, we hadn't found anything. And you might say, well, that was a waste of time. But in fact, that was an important result because at that time, as far as we knew, every star in the sky was transmitting signals. There were civilizations everywhere. This told us that was not the case. It was likely our search would be very difficult and might take a great deal of time. And as time has gone on, that has turned out to be true. Now, just to remind you why we believe that nevertheless searches are worthwhile, this is a picture I was describing to you right at the beginning. We believe that each star has around it a range of distances within which temperatures will be suitable for life. And by that we mean there will be on planets liquid water within this zone. Too close to the star, the water boils. Too far from the star, it freezes. The sun is a G-type star, so this shows you the ecosphere, as it's called, of the sun. That's what this donut represents. F-type star is a brighter star, has a bigger ecosphere. There aren't very many of those. The stars that are most numerous are here. The star doesn't even show. They're called M-type, and they are 80% of the stars in the galaxy or in the universe. They have a mass of 1/10 that of the sun, and a brightness about 1%, 1/100th that of the sun. And as a result, their ecosphere is very, very small. And it was thought that these would not be suitable candidates for searches because it would be very improbable that planets would be in this ecosphere. Now, of course, there's the possibility that the planetary system just scale down in proportion as the star's mass is less. And that has turned out to be true. That old idea that the M stars were out of the question has now died because we have detected planets around M stars, among those 400 stars mentioned earlier. And so nowadays it's considered okay to search life in G-type stars and E-type stars, and that's most of the stars in our galaxy. We've also learned other things, and that is that temperatures can be suitable for life at much greater distances from their star than in that old, very simple idea I just presented to you. And that's something we learned from Earth. You go up on mountains on the Earth, you often find snow on the top. You never find snow on the bottom and no snow on the top. I don't know if that's ever struck you, but that's the case. This is Mount Fuji in Japan. But why is that? It's because when you go upwards in an atmosphere, The gravity allows the air to expand, and it cools. Air expands, it cools if you compress it warm. And that's why it's always colder on the tops of mountains than down below. And what this tells us is that if we have a planet maybe too far from the traditional places where water would be present, but has a very deep atmosphere, as you go down in the atmosphere, it could get warmer and warmer until eventually you will get temperatures suitable for life. And indeed, in our own solar system, we have at least 5 planets where that has happened. The other extreme, by the way, is that the atmosphere can have a greenhouse effect, which traps the heat of the star and heats the planet much hotter than it should be at the distance it is from the star. And in our system, we have one of those. All these are lessons learned in our own solar system. And what we learned, which has humbled us, is that everything we needed to know about life in space we could have learned at home. It's like everything you need to know in life you learn in kindergarten. So it is with planets and life in the universe. This is Venus, almost twin to the Earth. It actually captures the same sunlight as the Earth, but the temperature on the surface of Venus is about 750 degrees. And that's a result of having a very dense atmosphere of carbon dioxide, so that the atmosphere is very deep, and when you go down, and the temperatures become that high. So no life on Venus. Well, that's bad news for Venus, but for Venus moved outwards, stay beyond the orbit of Mars, things will be good. So what this does is extend the distances within which planets would have temperatures on their surface suitable for life. Jupiter, giant planet, which is very bright in the evening sky now right after sunset. It's too bad it's cloudy tonight because it's right now as close to Earth as it comes. It would be a great sight through the telescope, and it'll be clear when we're done here. Jupiter has a very deep atmosphere. As you go down, the temperature rises and rises. It has many clouds towards the top of the atmosphere. As you go down, and you come to water clouds, ammonia clouds. They're clouds made of different chemicals. And in fact, if you go down far enough, temperatures are as in this room. If there were a surface there, life could exist on Jupiter. But there isn't one. Nevertheless, it has been proposed that perhaps life develops there anyway and actually floats. It evolves balloons, keep it at an altitude such that the temperatures are right for liquid water, and life may thrive there without ever being on a surface or in a liquid ocean. This particular picture, there's been a mountain added, and there may be planets like that, where there's just enough atmosphere to warm the atmosphere at the surface to suitable temperatures suitable for life, even though the planet is very far from Earth. These objects are named floaters, named by Carl Sagan with that name. In fact, that proposal was the first one ever published in the Astrophysical Journal. There would be planets with floating creatures that involve the ability to hold an altitude where life could exist in the planets. The planet Saturn has the same situation. Temperature levels where temperatures are suitable for life. Same with Uranus and Neptune. Down in the atmosphere, before you come to the surface, you come to levels where liquid water will exist. Another thing that we can make something habitable, which we never thought of, although it's been sitting there ever since the time of Galileo for us to study, is the satellite Europa of Jupiter. This is a picture of it. As you can see, it's kind of a bland object. You don't see craters or mountains or any of those things, telling us that the surface here is very fresh. And what is the surface here? We can tell from its spectrum that it's actually water ice. Just conventional water ice, the same thing occurs here in the winter. And in fact, the entire surface is ice. And not only is it ice, but we can see that it's not very thick. This is a close-up of the surface of Europa. And from here to here is about 2 miles. And you can see there are great chunks here, which sometime or other have broken off and have moved around, because you can see they can be matched like pieces of a jigsaw puzzle. And this tells us that the ice does not extend all the way to the surface. that at times there's melting so that we have, like the Arctic view of spring, ice floes floating in perhaps mushy water, and they move around, they break, they go like this. And by measuring the heights of these shadows, we can calculate how thick these ice floes are, because with an iceberg, which is what these are, about 1/10 of it protrudes from the water, and the other 9/10 is below the water. So when you measure the heights of these cliffs that you can see here, they turn out to be about 1 kilometer, half a mile high, which tells us that the ice blocks themselves are typically about 6 miles thick. So what this is telling us is that Europa is entirely covered by a sheet of ice which is about 6 miles thick. And data from the spacecraft tell us that below that ice there is an ocean, a liquid ocean of liquid water, which is about 150 miles deep. More water in Europa than in all the oceans of Earth. And it's liquid water, the right stuff for life. And so here, far out in the solar system, where the temperature on the surface is about 150 degrees below zero, there is in the ocean temperatures above the freezing point of water suitable for life. Could there be life there? That is one of our most interesting questions, which we all in space science would love to find out. Means sending a mission to Europa, drilling through the ice, and seeing what's in there. We know there's an ocean there.